Today we're going to work on Lab 5. It will be similar to Lab 2 because you're going to pass in on paper 2 data tables and 2 graphs, and you'll find a line of best fit and the slope of your second line. Don't forget your units. In this lab, you're going to work in groups of 3. Of course, if you prefer to do your own work, that's okay too. But each group of 3 will pass in one answer sheet. You will be provided with some ticker tape. What I'm actually going to do is I'm going to have a fake piece of ticker tape provided for you so it's a little easier to read. Using your ruler, you will record the distances just like you did with your previous ticker tape lab. And you will record the distance in centimeters and the time in seconds into a data table. Using your data table, you're going to create a graph on graph paper of your data. Remember, fill the whole page. Make this a big graph. It's much easier to read, and it's much more precise when you're trying to use the graph to extrapolate. What you should notice is that your data points are not in a straight line like they were in previous labs. And you're going to have to use the French curves to draw a line of fit. So watch the video on how to do that and how to use these curves. Then what you're going to do is using your data table and the formula, you're going to create second set of data from your first data table. I'll show you how. In a previous video, I showed you how to make a line of best fit. But when I did it with that data, those dots were all lined up in a pretty straight line, but you'll see from this data that it's not straight. It's not linear. So we can't use a regular ruler. We're going to use one of these. These are known as French curves. And what they have is they have a variety of different angles. The angle here is different than here. I guess the angle is not the right word, but the curvature here is different than the curvature there. And you can see all these circles and these loops, and there's different size ones. I've got a nice big graph here, so I'm going to use the largest of these curves, referred to as a French curve. So we can use it one side, or we could flip it over, use the other side. But what we want to try and do is find the best curvature that's going to bring us close to our dots. Usually what I do is I start with one dot near the end, and then I try to line up another dot at the other end and see if I can get the curvature to match. Sometimes if it's a little too big for the ruler, then maybe I'll use this dot here, and I'm going to try to line that up so that it fits pretty close. I'm getting close. I can see this is good. So right there is a pretty good curve for this part of my graph. So I'm going to draw my line. There's my line of fit. I need to extend that a little bit. It's not perfect, but I'll extend that to my last dot. It's not a perfect fit through here, but it's a nice curve in the early part. So I want to look closely at this curve. You'll see I've got a nice curve drawn here. What we want to do next is draw a tangent line. Now there's 2 ways we can do this. We can draw a tangent line or we can calculate. In this lab, we're actually going to calculate, but I want to explain what a tangent line is. So what a tangent line is a line that just touches this curve. So this is not a tangent line. Okay, it's not a tangent line because you can see it crosses my curve here and here. It crosses in 2 places. A tangent line will only touch in one place. So if I could pull that line down to a spot where it only touches in one place, that is a tangent line right here. And if we could find the slope of that line, we would know the instantaneous velocity at that point right there. So we will know how fast something is going at that point. Yes, there's a connection with tangent to your trigonometry unit of Math 10 when you learned about sine, cosine, and tangent. I won't get into that here. but that is the point that we're calculating an instantaneous velocity. And you'll notice that as we follow the curve, to do this properly, I would have to change the angle of my straight edge here to get a tangent line. Here, to get a tangent line, maybe it's this. And the slope of that line is very different than the slope of the other one. So we talked about finding the slope of a tangent line. Here's another way that provides us similar information. It's not quite perfect, but it'll work well enough for what we're doing. What we'll notice is that I've got my first data table here from my ticker tape. These are my observations. I have my time and I have my distance. And what I'm going to do is I'm going to create a second data table. And my times, I'm going to use the exact same time periods. And the reason I'm doing that, this is the times on the graph where we would have taken this is the point in the graph where we would have taken those tangent lines. I'm going to do a tangent line at time 0 and time 3, time 6, 9, and so on. And that is the moments where there's dots on our page. Now, once again, we knew that the slope of the first data table would give us our speed or velocity, and the units of that would be centimeters per second. Okay? So what we're going to do is we're going to look at what happened in this time interval right here. What happened in that time interval? And what we'll see is that the distance changed by 1 centimeter, and the time was 3 seconds. Now, when you pass in your data tables, don't have this numbers written in here, okay? I'm just showing you how I got it. So in this time interval, we had a change of 1 centimeter in 3 seconds. So the velocity, the average velocity from 0 to 3 would be 0.333 centimeters per second. Okay? What about in this time interval? In this time interval, our distance changed again by 1, and our time, once again, changed by 3 seconds. So you'll see that my velocity hasn't changed. You'll notice in the next time interval, this went up by 2 centimeters, still 3 seconds. So now you're going to see a different speed at that time interval, and that's that curve. It's not a straight line. It's not the same always. Now it's going up by 4 centimeters in a 3-second span. So that's going to be 1.333. This one went up by 8 centimeters in 3 seconds, and that's going to be 2.6. Okay, so we're using the time and the distance to calculate an average velocity of how much it changed, and we're going to record it over here. There was no change at the start because it hadn't moved, but then we're going to record this. Now what we're going to do is we're going to take this data table, we're going to graph that on a second graph, and we're going to find the slope of that line. Just very quickly, what would that look like? So once again, we're going to have our axes. You're going to use a full sheet of graph paper. Don't make a small graph like this. Once again, on the x-axis is time in seconds, and on the horizontal axis, we're going to have our velocity in centimeters per second. Graph it and find the slope of the line of fit.